Good evening, everyone. Let's just wait for 5 minutes so that people can join. Okay, so let's start. I hope my screen is visible now. I hope you all must have gone through the lecture videos of this week. Mainly, we started with the Bessel's function. So I'll just recall what the Bessel's function is and how what are its some of the properties. So let's just recall that Bessel's function are basically the solution of the differential equation of the form x square y double dash plus xy dash plus x square minus alpha square y equals to 0. Corresponding to different alpha, we call J alpha, which is a solution of 1 is called Bessel's function. The general representation for Bessel's function is given by J alpha x is equal to summation r from 0 to infinity minus 1 to the power r factorial gamma alpha plus r plus 1 and x by 2 to the power 2r plus alpha. Then we have some basic properties of the Bessel's function that we'll be using to solve today's tutorial questions. So properties, or we can say the recursion formula, its properties of G. First one is d by dx of x to the power n j n ax is equal to ax to the power n j n minus 1 ax. I hope you all must have seen the proof of these properties in the lecture notes. It was done in the class. Second property, sorry, x to the power alpha j alpha x is equal to x to the power alpha j alpha minus 1x. The second property is d by dx x to the power minus alpha j alpha x is equal to x to the power minus alpha j alpha plus 1x. Also, we have property, you can call it as value for a fixed alpha. We know that for alpha equals to 1 by 2, that is j 1 by 2 x is given by under root 2 by pi x sine x. So we'll be using these properties mainly and the general formula for the Bessel's function to solve the questions today. So let's start. First question. Show that j minus nx equal to minus 1 to the power n j nx, where n is a positive integer. So we'll be using the basic general formula for the Bessel's function and for alpha equals to nn minus n and manipulate them in such a way so that they both satisfy this equation. So the main properties that we will be using are, first of all, gamma n plus 1 is equal to n factorial. Yes, this is the main property that we will be using. Also, we if you all can recall that gamma of minus n, let's write it as minus k, for any integer, this is not defined. So or we can say is, it's basically infinity or minus infinity, so it is not defined, is not defined for every k being natural number. This would give us that 1 by k would tend to 0, or can be written as equal to 0. So we'll be using it. Let's see how. Proof. So now we know that j minus nx, just replacing alpha by minus n in the general formula for the basis function, we'll get summation r equals to 0 to infinity minus 1 to the power r factorial. I hope I had written r factorial. Yes. Gamma minus n plus r plus 1 x by 2 to the power 2r minus n. Now, if we know that 1 upon gamma minus n plus r plus 1 would be 0 whenever this term is negative. This term is negative means for every r equals to 0, 1, 2 up to n minus 1. Yes. For r strictly less than n, for r less than equal to n minus 1, na? This is 0. So that means we can remove the first n minus 1 terms in the summation. So this gives us j minus nx is basically summation r from n to infinity minus 1 to the power r factorial gamma minus n plus r plus 1 x by 2 to r minus n. Now let's take m to be equal to r minus n, that is r equals to m plus n. We'll be just shifting the series, or we can say we are doing a substitution in the series. So instead of r we have m, which is from 0 to infinity minus 1 to the power m plus n. Then we have m plus n factorial. Then we have gamma at this n and minus n would be cancelled out. We'll be left with m plus 1 x by 2 to the power 2m plus 2n, and minus n will give us plus n. Now since this n is independent of the summation, we can take minus 1 to the power n outside. We have summation m from 0 to infinity minus 1 to the power m. Now m plus n factorial is basically gamma m plus n plus 1, and gamma m plus 1 is m factorial x by 2 2m plus n. Now this is the definition for Jn. This is minus 1 to the power n Jnx, because what was Jnx? Jnx was, if instead of r we write m from 0 to infinity minus 1 to the power m factorial gamma m plus n plus 1 x by 2 2m plus n. Therefore, we get j minus n because we started with j minus n and at is equal to minus 1 to the power n j n x. I hope the solution was fine with everyone. Just go through it again, and if you have any doubt, please let me know. Let's move to the next question. Show that d by dx to the power n j n ax is equal to ax to the power n j n minus 1 at ax. Here also, we'll start with the general expression for the Bessel's function. We have jnx is equal to summation r from 0 to infinity minus 1 to the power r factorial gamma at n plus r plus 1 r by 2 to the power x by 2 to the power 2r plus n. This gives us x to the power n times j n ax is equal to, we'll just multiply it with x to the power n and replace, and here will replace x by ax. So that would give us summation r from 0 to infinity minus 1 to the power r 1 this x to the power n by r factorial gamma n plus r plus 1, and here instead of x we have ax by 2. 2r plus n. Now we need to find its derivative. So let's just combine all the powers of x. We'll have r from 0 to infinity minus 1 to the power r, a to the power 2r plus n, x to the power 2r plus n would give us 2n by r factorial 2 to the power 2r plus n gamma n plus r plus 1. Now all the terms are constant except for x to the power 2r plus 2n. So since this is a this is a series with exponents of x, we can easily differentiate it term by term. So we'll get d by dx of x to the power n j n ax is equal to summation r from 0 to infinity. Constant terms will remain as it is. Then we'll have 2 times r plus n, x to the power 2r plus 2n minus 1 by r factorial 2 to the power 2r plus n gamma at n plus r plus 1. So on the right hand side, we want some j n minus 1 at ax. So let's see how does it look like. So this was our left hand side. Now let's see. Let's mark it as number 1. So now our right hand side was a x to the power n j n minus 1 x. Yes. So this is a x to the power n summation r from 0 to infinity minus 1 to the power r, sorry, by r factorial gamma n minus 1 r plus 1 would give us n plus r, x by 2 to the power 2r plus n minus 1. So see, here the powers of x are fine. We need okay, so right hand side it was j ax, yes. So let's combine all the terms involving a and x. We'll get summation r from 0 to infinity minus 1 to the power r, a to the power 2r plus n. Then we have x to the power 2r plus 2n minus 1 by r factorial 2 to the power 2r plus n minus 1. Now here we have gamma n plus r, but earlier we want something of the form gamma n plus r plus 1. So we know that gamma n plus 1 is n times gamma n. So we can write gamma n plus r to be n plus r by gamma n plus r plus 1. Because gamma n plus r plus 1 would be n plus r times gamma n plus r, and this n plus r in the denominator will get cancelled out to the one n on the numerator side. And also, instead of taking this to be minus 1, we'll just take it in the numerator. So now you can see that we are in the same framework as that in the left hand side. Minus 1 to the power r, a to the power 2r plus n, x to the power 2r plus 2n minus 1, 2 times n plus r upon r factorial, 2 times 2 to the power 2r plus n, and gamma n plus r plus 1. So this is equal to by equation 1. And that is what we wanted to prove. Therefore, d by dx of x to the power n ax is equal to a x to the power n minus 1 j n minus 1 ax. I hope this solution was fine with everyone. I would like you to just go through it once again, and if you have any doubt, please let me know. Let's move to the next question. Find the differential equation satisfied by fx is equal to under root x by j 1 by 2 x. So we all know the value of or we can say the expression for j1 by 2x. So we'll just have to check what kind of differential equation it satisfies. We know that j1 by 2x is equal to under root 2 by x pi sine x. So this gives us under root x pi j1 by 2x is equal to root 2 sine x. So this was our fx. Now we need to see what differential equation the function fx is equal to root 2 sine x satisfies. So we have f dash x is equal to root 2 cos x, which gives us double derivative of f is equal to minus root 2 sine x, which is minus fx. So this implies f double dash x plus fx is equal to 0. Therefore, f satisfies the following differential equation, which is y double dash plus y is equal to 0. I don't think there was much technicalities in this question. Just go through it once again. If you have any doubt, please let me know. Let's move to the next question. Show that Jn times j minus n dash minus j minus n times j n dash is equal to sine minus 2 sine n pi by x pi. Here n need not be integer. If it was integer, then directly we have sine n pi equals to 0. We are talking about any general n. solution. So now we know that Jn is solution of Bessel's equation. So that means this Jn would satisfy, since Jn and J minus n are solutions of their corresponding Bessel's equation, this implies Jn would satisfy corresponding to alpha equals to n, and since we have alpha square in the given problem, so and since n and square of n and minus n are same, so they are basically satisfying the same equation. So this would give us x square j double dash plus x jn dash plus x square minus n square jn is equal to 0, and x square j minus n double dash plus x j minus n dash plus x square minus n square j minus n is equal to 0. Let's number this as 1 and 2. Now we'll multiplying first by j minus n and second by j n, and then subtracting, we will get x square j n double dash j minus n plus x j n dash j minus n plus x square minus n square j n j minus n is equal to 0, and x square j minus n double dash j n plus x j minus n dash j n plus x square minus n square j n j minus n is equal to 0. Now subtracting these two equations, this will be cancelled out. So we'll be left with x square j n double dash j minus n minus j n double j minus n double dash j n is equal to, taking the rest of the term on the other side of the equation, j n dash, sorry, j minus n dash j n minus j n dash j minus n. So this x gets cancelled out. Now if we define this to be equal to some other function v, we get vx is equal to j n double dash j minus n minus j minus n double dash, sorry, we will define vx equal to j n dash j minus n minus j minus n dash j. So this gives us v double dash x is equal to, let's number this one as well as equation 3. From here, let's just differentiate both the side. We'll get j n double dash j minus n plus jn dash j minus n dash minus j minus n dash jn dash minus j minus n double dash jn. So these two terms gets cancelled out, and this is jn double dash j minus n minus j minus n jn. So by equation third, this is equal to 1 by x times j minus n dash jn minus jn dash j minus n by equation third. And this is equal to minus vx by x. So we have a not double dash, just one derivative. So we have a differential equation in variable for dependent variable v. We have dv by dx is equal to minus vx by x, which is basically d e is equal by v is equal to minus dx by x. This is just a separation of variable case. We can solve this differential equation and we'll get ln v is equal to minus ln x plus some constant. We'll take that constant to be ln c. This gives us vx is equal to c by x. Now again, by the definition of vx, what was vx? Vx was jn dash j minus n minus j minus n dash jn is equal to c by x. Now we'll just evaluate the value of jn dash, j minus n and j minus n dash, and then we'll put them on the right hand side, and after that we'll be comparing the coefficients of 1 by x on both the sides and hence find the value of c, because you can see that what we need to prove on the left hand side, it's negative of vx in the left hand side. On the right hand side we have 1 by x times some constant, so we need to find this constant. So now we know that jnx is equal to summation r from 0 to infinity minus 1 to the power r factorial gamma n plus r plus 1 x by 2 to the power 2r plus n. So now if I expand this, we'll get x to the power n r equals to 0 by 2 to the power n gamma n plus 1 minus x to the power 2 plus n by 4 times gamma n plus 2. Gamma n plus 2 can be written as n plus 1 factorial times gamma n plus 2 can be written as n plus 1 times gamma n plus 1, n plus 1 times gamma n plus 1, yes, and so on. So I'll just take the coefficient. I'll take common x to the power n by, also we had, this is we'll have 4. This is basically 2 to the power 2 plus n. So we can take out common 2 to the power n, gamma n plus 1, and rest will be left with 1 minus x square by 4 n plus 1, or it will be, will need this x to the power n inside. You'll see further why we are doing this, and so on. Similarly, this is jn x, that would give us jn dash x is equal to 1 by 2 to the n gamma plus 1 as it is. So we'll have n x to the power n minus 1 minus 2 plus n x to the power n plus 1 by 4 n plus 1, and so on. Similarly, we'll get j minus n x is equal to minus n gamma 1 minus n x to the power minus n minus x to the power 2 minus n by 4 1 minus n, and so on, and that would give us j. I have just here replaced n by minus n to find the value of j minus nx. These are basically, I am just expanding the series. So because we want to know what will be the coefficient of 1 by x, so we'll be just multiplying j n x by derivative of j minus nx and whatever that was required. So from here we'll get uh, j dash minus n x equals to 1 by 2 to the power minus n gamma 1 minus n n x to the power minus n minus 1 minus 2 minus n x to the power minus n plus 1 by 4 1 minus n, and so on. So this implies c by x, which was equal to c by x was equal to j n dash j minus n minus j minus n dash j n is equal to, now let's see, j n dash and j minus n. Outside will be left with gamma n plus 1 times gamma 1 minus n, because 2 to the power n and 2 to the power minus n would be cancelled out, and n x to the power n minus 1 minus 2 plus n x to the power n plus 1 by 4 n plus 1, and so on, times n x to the power minus n minus 1 minus 2 minus n x to the power minus n plus 1 by 4 1 minus n, and so on, minus, now we'll see the terms, j minus n dash, okay, that was j minus n, so this was j minus n is x to the power minus n minus x to the power 2 minus n by 4 times 1 minus n, and so on. Now we'll see j minus derivative of j minus n and jn, these two terms. So this will give us 1 by gamma n plus 1 gamma 1 minus n, because again we have 2 to the power n and 2 to the power minus n, that would be cancelled out. Rest Next we'll have n x to the power minus n minus 1 minus 2 plus n x to the power n plus 1 by 4 n plus 1 and so on. The second term would be Jn x to the power n minus x to the power 2 plus n by 4 n plus 1 and so on. Now all we need is the coefficient of 1 by x. So from the first this product we can see that while multiplying this first term with rest of the terms, the value x to the power 1, x to the power minus 1 would be the first term and rest of the terms will have higher powers of x. So we'll just have this first term from this part and first term from this part as the coefficient of 1 by x. So comparing the coefficient of x to the power minus 1 on both sides, we'll get c is equal to, so from the first term we'll get n by gamma n plus 1 times gamma 1 minus n. So there was a minus n, no? This one j, oh, j minus n dash. This was, this was minus n. Plus n times n upon gamma n plus 1 times gamma 1 minus n. So this is basically 2n times gamma n plus 1 gamma n minus 1, which is again gamma n plus 1 is n times gamma n. So 2n by n gamma n times gamma 1 minus n. This n gets cancelled out. We have 2 by gamma n gamma 1 minus n. Now you can, if you remember, this gamma n times gamma 1 minus n is basically beta n 1 minus n. So this is basically 2 by beta n 1 minus n, which is, and we know that beta alpha 1 minus alpha is pi by sine pi x. So sine pi alpha. So in this case we'll have pi by sine n pi. So therefore our C is equal to 2 sine n pi by, now putting this value of C in the equation, where was it? Let's mark this as number 4, this as number 5. Using equation 5 in 4, we get j minus n dash j n minus j minus n j n dash is equal to, what was our v? V was j n dash times j minus n. So negative of this is equal to c, which is 2 sine n pi by pi x. Therefore, this is what we wanted to prove. We wanted to prove Jn j minus n dash minus Jn dash j minus n is equal to minus 2 sine n pi by pi x. I hope this solution was fine with everyone. It was quite complicated. All you need to do is expand the series sum of the Bessel's function take its derivative, then multiply. After multiplying, you will see that only the first term would give us 1 by x, rest of the term would give higher powers of x. So, and since we wanted just the coefficient of 1 by x, that would be easier. And another important thing to remember in this question was that we need to take this function to be Vx. Let's move to the next question. Question number 5. Show that relation 0 to pi by 2 root pi x j 1 by 2 2x dx is equal to 1. Again, we'll be using the standard expression for j1 by 2x. Solution. We know that j1 by 2x equal to root 2 by x pi sin x. So this gives us root pi x times j1 by 2x is equal to root pi x times root 2 by, so this x would be replaced, sorry, we want j1 by 2 at 2x. So this x will be replaced by 2x pi times sine 2x. So this gets cancelled out, this gets cancelled out. We are left with sine 2x. Now this gives us integration 0 to pi by 2 root pi x j 1 by 2 2x dx is equal to 0 to pi by 2 sine 2x dx. Now we know that integration sine x is minus cos 2x by 2, 0 to pi by 2, taking minus 1 by 2 outside. Sine pi is minus 1, minus sine 0 is 1. So we have 1. If you have any doubt in this question, please let me know. Let's move to the next question. Question 6. Show that d by dx of j, sorry, x j2x is equal to x j1x minus j2x. Now we'll be using the recursive property of Bessel's function that we had recalled in the starting of the session. So we have d by dx x j2x. It can be written as d by dx x to the power minus 1 x square j2x. Now we'll apply the product rule. X to the power minus 1 as it is, derivative of the second term j2x plus x square j2x as it is, derivative of x to the power minus 1 would be minus x to the power minus 2. Now this is equal to x square j1x plus minus j2x. Why? Because we have d by dx of x to the power alpha j alpha x is equal to x to the power alpha j alpha yes, we have alpha minus 1x. Let's recall this by the first property. Now this gives us x minus j2x. That is what we wanted. I hope this was clear. If you have any doubt, please let me know. We have mainly only used the first property that we had listed in the starting of the session. First property of Bessel's function. Let's move to the next question. Question 7. Show that two times d by dx of j2x is equal to j1x minus j3x. We'll be again using the recursive formula for the basis function. Solution. We have the left hand side 2 d by dx 2x. It can be written as d by dx j2x, because on the right hand side we need j1 and j3. That means we are decreasing the value of n as well as increasing the values of n. So we'll just split this into two parts and use both the recursive formulas simultaneously. Plus d by dx j2x is equal to, now with j2 we need x square, so we'll just multiply it by x square and x to the power minus 2 plus d by dx x to the power minus 2 x square j2x. Next we'll apply the product rule, just differentiating it. So we'll have x to the power minus 2 as it is, d by dx of j2x plus x square j2x as it is. Derivative of x to the power minus 2 would be minus 2 x to the power minus 3. Similarly for the second term, x to the power minus 2 as it is, d by dx x square j2x. Sorry, this time we will need x to the power minus 2. So we'll take it to be like this. Because to decrease we need x square, but to increase we need x to the power minus 2. So remember this formula. See here the property. To decrease the value of alpha, to move from alpha to alpha minus 1, we need the coefficient x to the power alpha. But whereas when we are increasing the value, increasing this alpha to alpha plus 1, here we have x to the power minus alpha. So let's just manipulate our left hand side so that we can use it. Plus x to the power minus 2 j2x as it is. Derivative of x square would be 2x. So this is x to the power minus 2. Now by first property, d by dx of x square j2x is x square j1x plus, sorry, minus, this is 2x to the power minus 1 j2x plus, again we'll have minus this side, minus x square as it is, d by dx of x to the power minus 2 j2x would be minus of x to the power minus 2 j3x plus 2x to the power minus 1 j2x. Now this gets cancelled out. We are left with j1x minus j2x. Sorry, j3x. That is what we wanted. RHS. I hope this was clear enough. If you have any doubt, please let me know. Let's move to the next question. Number 8. This would be our last question of this tutorial sheet. So again we'll have to use the recurrence formula. Make use of recurrence formula to evaluate integral x cube j3x in terms of j0, j1 and j. Solution. So let's start with integral x cube j3x. So to come back to lower alphas, that means to j0, j1, j2, we will have, so we want this j3 to be something of the form d by dx of some x times j2x. Then only we can go to lower j, lower value of alpha. So we'll write this to be equal to x power 5, x power minus 2, j3x. Now this is equal to d by dx of x power minus 2 j2x by the second property of the basis function that we have discussed in the starting of the session. So this is x to the power 5 d by dx of x power minus 2 j2x. Now this can be written as derivative of the whole term x power 5 x power minus 2 j2x minus the derivative of x to the power 5, 5x to the power 4 and rest of the term as it is. This is basically the product rule. So we get from here d by dx, integral of d by dx of x cube j2x minus 5 integral of x square j2x dx. Now this integral and derivative gets cancelled out. We are left with x cube j2x minus 5 times. Now from x2 to now we want to move from alpha equals to 2 to alpha equals to 1. So we'll write it as x cube x power minus 1 j2x dx. So this was minus here. So we'll have a minus here, a minus here, a minus here, and a plus here. Minus plus. So this is equal to minus x cube j2x plus 5. Now this term is equal to minus d by dx of x square, x bar minus 2. X bar minus 1 j1x. So this plus gets minus x cube d by dx of x to the power minus 1 j1x. Again by product rule, we'll get x cube j2x minus 5 integration d by dx of x cube x power minus 1 j1x minus derivative of x cube 3x square and rest of the term as it is dx. So this implies we have minus x cube j2x minus 5x square j1x plus 15 integration x j1x. Now we'll move from j1 to j0. So this can be written as minus x cube j2x minus 5x square j1x plus 15 x power 0 j1x dx, which is equal to minus x cube. Now this term is equal to minus d by dx of x to the power 0 j 0x. So this is equal to minus x cube j2x minus 5x square j1x minus 15 x d by dx of j0x dx. Now again by product rule, we'll get minus x cube j2x minus 5x square j1x minus 15 integration d by dx of x j naught x minus derivative of x is 1 and j naught x as it is dx. So this is equal to minus x cube j2x minus 5x square j1x minus 15. This derivative and integral cancels each other. We're left with x j naught x plus 15 j naught x dx. Sorry, here we don't have the integral and here we will have the integral. And what was on the left hand side? Integral x cubed j 3x. I hope this solution was fine with everyone. We have mainly used the recursive formula for the Bessel's function repeatedly. If you have any doubt, please let me know. I'm waiting. Okay, then we'll meet next week. We'll be discussing the questions related to the further topics that will be discussed in the class. Okay, thank you.